So still talking about colligative properties, next we have osmotic pressure. Okay, so osmotic pressure, right? We're going to talk about a couple different things. So let's look at this graph, right? So in this graph, we got our pure solvent on our left side. We got on the right side a solution. And in the middle, we got this membrane that's being a barrier between both of them, okay? Now in this case, it's a barrier, but, right? Certain things can get through. Okay, so certain things can get through. Okay, so this is semi-permeable. Okay, so it's basically one through which the solvent, but not the solute, can pass. So the solvent can get through, but the solute cannot. Okay, semi. Now, with osmotic pressure, okay, we're going to see something that we call osmosis. So osmosis is basically when our pure solvent will flow through this membrane, okay, into the solution of the same solvent. So this is the same solvent over here with the pure solvent. Okay, it's the same solvent. So we got osmosis going on. The pure solvent is flowing through this membrane, okay, into the solution. That's what we're saying, osmosis occur. Now, eventually, all right, equilibrium will be reached. Okay, so we're going to reach that point of equilibrium. And once we reach that point of equilibrium, right, where our rates are going to be the same in this case, okay, the pressure from the solution side, so the pressure from the solution side will be greater than the pure solvent side. Osmotic pressure, once again, we can just think of this term as the minimum pressure needed to stop osmosis. So once we get to osmotic pressure, notice, right, no more osmosis is going on, right? We're not going to get any more pure solvent going through here because it's reached its point. It's at equilibrium. It's done, okay? It's done. It's over. With osmotic pressure, let's talk about a couple different things. So let's just focus on. Let's go straight to the equation. Osmotic pressure is, all right, we got our pi equals mRT. Big M is molarity, so do not confuse this with molality. We got big M here. We got R. Y'all remember that? That's ideal gas constant. And then we got our T. That's our temperature, and that's usually going to be in kelvins. Now, this is our equation. We'll get to some problems later on, but this is the equation for osmotic pressure. Now, we can see a couple examples of this in everyday life, right? Dialysis, right? Dialysis is actually a form of osmosis of the solvent. Osmosis of solvent plus small molecules, right? So when we think about dialysis, we understand that that's used to purify the blood of people with like kidney problems, right? So this is a form of osmosis. Another form of osmosis is you can actually reverse it. Okay, so reverse osmosis is when the external pressure causes the flow from the solution to the solvent, right? So in this case, reverse osmosis would be applying pressure, forcing this back through the membrane over to this pure solvent side. Now, we see this reverse osmosis. Recently, we've been seeing it with producing drinking water from seawater, right? Because in this case, the solution is the seawater. We're going to reverse osmosis it, right? Apply pressure, apply that energy, and then now it's pushing, right, separating the salt from the water. And then guess what we're getting on this side? Pure solvent, right? Drinking water. Now, this is how we're seeing that, right? But if you understand reverse osmosis, you also understand that this needs a lot of pressure. It needs a lot of pressure. Even for this instance right here, this example, if you looked at, these type of machines that they're using, it requires a lot of energy to do this reverse osmosis, right? Very hard to do. But this is what we see on a typical everyday, okay? And once again, we got our equation with the pi equals mRT, okay?